Come in a little. Okay. Move back about a quarter of an inch. Move back. More. Okay. I did it. Level of the air to the level of the air. Okay. Listen. Good. Withdraw. We just made a transfer of some liquid helium out of a storage tank into our own experimental equipment. Helium is a remarkable substance. It has two different and easily distinguishable liquid phases, a warmer and a colder one. The warmer phase is called liquid helium-1, and the colder phase, liquid helium-2. The two phases are separated by a transition temperature, known as the lambda point. When liquid helium is cooled down through the lambda point, a transition from helium-1 to helium-2 is clearly visible. We will show it to you later in this film. The two liquids behave nothing like any other known liquids, although it could be said that helium-1, the warmer phase, approximates the behavior of common liquids. But it is helium-2, the colder phase, which is truly different. Because of this, it is called the superfluid. The temperatures involved when working with liquid helium are quite low. Helium boils at 4.2 degrees Kelvin under conditions of atmospheric pressure, and the lambda point lies at roughly 2.2 degrees. Note that this corresponds to minus 269 and minus 271 degrees centigrade. The properties of liquid helium that I have just been telling you about are characteristic of the heavy isotope of helium, helium-4. The element occurs in the form of two stable isotopes. The second and lighter one, helium-3, is very rare. Its abundance is only about 1 part out of 10 million. Pure liquid helium-3 is the subject of intensive study at the present time, but so far, no second superfluid liquid phase has been found to exist for helium-3. The low temperatures at which we'll be working call for well-insulated containers. The doer meets our requirement. The word doer is the scientific name given to a double-walled vessel with the space between the walls evacuated. When these dewars are made of glass, the surface of this inner space is usually silvered to cut down heat transfer by radiation. However, our dewars will have to be transparent so that we can look at what's going on inside. Now, liquid helium is commonly stored in double dewars. The design is quite simple. Just put one inside the other, like this. In the inner dewar, we put the liquid helium, and in the space between the inner and outer dewar, we maintain a supply of liquid air. Here is a double dewar, exactly like the one we will be using in our demonstration experiments. The inner dewar is filled with liquid helium. The outer dewar contains liquid air. The normal boiling temperature of liquid air is about 80 degrees Kelvin, 75 or more degrees hotter than the liquid helium. The purpose of the liquid air is twofold. First, we put the liquid air in the outer dewar well ahead of putting liquid helium in the inner dewar. In this way, the inner dewar is pre-cooled. Secondly, we maintain a supply of liquid air in the outer dewar because it provides an additional mantle of insulation now that the liquid helium is in the inner dewar. The boiling of the liquid air attests to the fact that it is absorbing some of the heat which entered the double dewar. Even with the boiling of the liquid air, the liquid helium is clearly visible. Later, we will use liquid air cooled below its boiling temperature to reduce or eliminate the air bubbles for better visibility. Now the liquid air is cooled down and we have eliminated boiling. The smaller bubbles of the boiling liquid helium are clearly visible. The cover over the inner dewar has a port, at present open. The liquid helium is at atmospheric pressure, so its temperature is 4.2 degrees Kelvin. In other words, what we have in here now is liquid helium-1, the warmer of the two phases. Before we cool it down, to take a look at the superfluid phase, I want to dwell briefly on the properties of helium-1. I've told you before that even helium-1 is different from the normal liquids. The distance between neighboring atoms in this liquid is quite large. The atoms are not as closely packed as in the classical liquids. The reason for this is quantum mechanical. The zero-point energy is relatively more important here than in any other liquid. As a consequence, liquid helium has a very low mass density, only about 13% the density of water, and a very low optical density. The index of refraction is quite close to 1. This makes its surface hard to see with the naked eye under ordinary lighting conditions. You are no doubt familiar with the fact that the helium atom has closed shell atomic structure. This explains why helium is a chemically inert element. It also accounts for the fact that the force of attraction between neighboring helium atoms, the so-called van der Waals force, is small. It takes little energy to pull two helium atoms apart, as for example, in evaporation. This gives liquid helium a very small latent heat of vaporization. Only 5 calories are needed to evaporate 1 gram. Compare this with water, where evaporation requires between 500 and 600 calories per gram. The low van der Waals force, combined with a large zero-point energy, also account for the fact that liquid helium does not freeze, cannot be solidified at ordinary pressures, no matter how far we cool it. However, liquid helium has been solidified at high pressure. The liquid helium in the dewar is at 4.2 degrees. We now want to cool it down to the lambda point and show you the transition to the superfluid phase. Our method will be cooling by evaporation using a vacuum pump. Now, the lambda point lies at 2.2 degrees, only 2 degrees colder than the present temperature of the liquid. What's more, not very much heat has to be removed from the liquid helium now in the dewar to bring it to the lambda point. It amounts to only about 250 calories. Nevertheless, don't get the idea that this cooling process is easy. On the contrary, it's quite difficult. More than 1/3 of the liquid helium now in the dewar has to be pumped away in vapor form before we can get what remains behind to the lambda point. That requires an awful lot of pumping and explains why we use this large and powerful vacuum pump over here. Even with this pump, the cooling process takes a considerable amount of time. Why it is so difficult to cool liquid helium to the lambda point. I have already mentioned that liquid helium has a remarkably small heat of vaporization, only 5 calories per gram. At the same time, liquid helium at 4.2 degrees has a high specific heat, almost 1 calorie per gram. Therefore, 1 gram of the vapor pumped away carries with it an amount of heat which can cool only 5 or 6 grams of liquid helium by 1 degree. That's not very much cooling. It is less by a factor of almost 100 than when we cool water by evaporation. The situation gets even worse as cooling progresses below 4.2 degrees, because the specific heat of liquid helium rises astonishingly as we approach 2.17 degrees, the lambda point. The heat of vaporization, on the other hand, remains roughly the same. So, a given amount of vapor carried off produces less and less cooling as we approach 2.17 degrees. Our thermometer here is a low pressure gauge connected to the space above the liquid helium. The needle registers the pressure there. It is the saturated vapor pressure of liquid helium. The gauge is calibrated to the corresponding temperature. We call it a vapor pressure thermometer. As we approach 2.17 degrees, boiling becomes increasingly violent. Suddenly it stops. This was the transition. The liquid you now see is helium-2. Even though evaporation does continue, there is no boiling. Normal liquids, such as the water in this beaker, boil because of their relatively low heat conductivity. Before heat, added at one point, can be carried away to a cooler place in the liquid, bubbles of the vapor form. Helium-1 behaves like a normal liquid in this respect. The absence of boiling in helium-2 reveals that this phase acts as if it had a large heat conductivity. As a matter of fact, as the liquid helium passed through the lambda point transition you just saw, its heat conductivity increased by the fantastic factor of 1 million. The heat conductivity of helium-2 is many times greater than in the metals silver and copper, which are among the best solid heat conductors. And yet, here we deal with a liquid. For this alone, helium-2 deserves the name of superfluid. Actually, the way in which helium-2 transports such large quantities of heat so rapidly is totally different from the classical concepts for heat conduction. I'll come back to the subject later in connection with an experiment demonstrating the phenomenon of second sound in helium-2. Remember that this